Hello, everyone. My name is Vukasin, and I'm the founder of Tesla Nation. Thank you all for joining us for this event of ours tonight, one in the series in which we look at technical solutions that professionals and teams from Serbia can create to leverage technology for, well, I'm going to say the benefit of mankind. That insight that there is a huge breadth and width of talent in Serbia when it comes to creating global technical solutions that can really make a great difference was the impetus for us to start Tesla Nation, the project for promoting innovation and technology that comes from Serbia that is globally applicable. And tonight, I think we have a really, really amazing session where we will be looking at a technical solution that has been created in order to leverage one of probably the most important industries of today, and that is renewable energy. And we are very, very lucky to have with us Ognjen from Kotek, who will be sharing their case study from a project they did on how to optimize the workings of a wind turbine with the application of AI. So thank you all for being with us, and I'm gonna hand it over to you, Ognjen. Thank you so much for making the time to make the presentation and join us tonight.
Hi, thanks, Vukasin. It's my pleasure to be here. My name is Ognjen Bjelica, and I'm joining you tonight in front of Kotek to basically share an experience that we recently had. We are going to talk about the project that I think might be interesting to most of the developers out there, because the idea behind the project, as exciting it is, you will see there have been quite a few things that we have developed in meantime that might be applicable to many other fields and projects out there. We are going to talk about how did we design hardware and software solution for automated inspection of wind turbines from basically an embedded device, using, of course, artificial intelligence to help us through that process. So the brief story behind the project. What is TMC? The idea behind the TMC is that we want to have an automated way to help troubleshoot wind turbines and detect any issues or point of failures that might happen in the future, and in a cost-friendly way deal with that earlier than having to basically solve the issue when it's too late, or deal with the issue when it's too late. This project was in making for a couple of years before we joined. And when we joined, of course, we did the evaluation of the current state of the project. And even though there were quite a few good things inside the project, we decided to go from scratch and to use that project as a guideline, because at the end, the project wasn't in a phase where it could actually do what it was supposed to do. And as I said again, the idea was that we are going to mount the camera somewhere at the bottom of the tower. And then we want to scan basically the entire length of the blade by capturing series of images from a position near the ground. And in a later slide, I'm going to show you just how tall these structures can really be. Regarding the components that were involved, we had quite a few components that needed to talk to each other. So we had a single board computer, which was actually a brain inside the TMC device. And then we had a gimbal. That's actually a device that is able to point to the camera at basically desired angle. And we also had to implement that movement or logic for controlling that custom-made device. We also had to talk with the commercial-made camera. So that could be a Canon or Nikon or any basically camera that can fulfill the features that we needed from it. And that was pretty much the image quality and to use high power lens, because some of these distances can be 150 meters plus. So we need to take a crisp image at huge distance. We also needed to include different sensors to tell us, is the device ready to operate in those conditions? Is it raining? Is it too cold? Or maybe its lens is getting foggy, we need to clean it. And we had quite a few challenges in the entire process. We also needed to expose certain interfaces, basically for a mobile application to be developed, or for a web application, or for desktop application. And in any case, we needed a way for our device to communicate with other devices as well. Now, on this image in top right corner, you can see basically a perspective that a TMC would see. It's not exactly the same because field of view here is much wider, but you get the idea what we were trying to do. Beneath that, you have a high-level overview of all the components that we needed to develop, and they are basically divided into two blocks. One is components that are going to be run on a single-board computer, and the other one, the components that will be run on a custom-made electronic, or in this case on PLC. So we needed to expose REST APIs. We needed ability to access this device remotely, because at the end, these devices are usually mounted somewhere where it's not where they are not really accessible. Like, you will not find them in the center of a city. You will find them in the middle of the ocean. You will find them on mountains where there is a lot of wind, because their job is to produce a lot of energy. We also needed ability to upload a new version of the firmware, again, remotely. We needed to talk to the turbine, because in the turbine niche, there is a lot of also complex electronics that is running the entire thing and making sure that it can operate non-stop. And again, there is the camera and there is the AI. At the end, we needed to integrate the AI also in our device itself, because if you imagine going in the middle of the ocean to inspect tens of these wind turbines, and then after a couple of days you return back home and discover that some of the images or most of the images are out of focus or do not have satisfactory image quality, then nobody would be happy. So what were the challenges that we faced here when we started? As I said, the project was already in the making. When we joined, we decided to go from the scratch. And the issue was that even though it was in the making for quite some time now, most of the components were not ready. So we needed to start developing, for instance, algorithm that will enable us to follow the curvature of the blade. And these things are anything but straight. They are really curvy. So we needed to develop algorithm for that, but most of the components were not ready or will not be ready in next half of year or something like that. And anyone who is familiar with the Agile framework basically knows about the Agile principle, where you are always trying to develop, to improve what you are building, and you are always trying to develop small increments of your project. But the issue is, how are you supposed to develop something like that or apply something to that, and not only to a sprint level, but to incorporate that in every single task that you are doing. So how can you get immediate feedback without actually having to go on the field? What can be visualized, what we can unit test, and so on. So what we did, basically, as I said, evaluated existing solution, but that's something that anyone who was in software development for more than 2 years had an opportunity to do. we actually decided to develop a 3D simulator. Why? Because we needed to see what the camera is going to see. We needed ability to talk to a device that's still not ready, or it's still not made. It wasn't even designed fully. And we needed a way to verify that, yeah, our ideas are actually manageable. And we actually ended up in building a whole set of tools that are going to help us, like a remote controller app, live view app, PLC simulator, and I will mention each and one in a bit more details. So a 3D simulator is basically a game where you have a wind turbine or 3D model of a wind turbine, and then you can basically do whatever you want to do with that simulator. For instance, making a gimbal or ability to position camera in a 3D simulator is relatively easy thing to do. All you have to do is just rotate it. In real life, you have to design it, you have to manufacture it, you have to purchase different parts, and etc. So we also had to basically solve an issue: how do we integrate a game with another software? Because games are usually meant to be either single or multiplayer. But if multiplayer, they are mostly used to communicate with the same instance of a game on another PC. So we needed a way to expose our basically endpoints to other applications. Now we decided to go with Unity 3D framework or game engine because, yeah, the rest of our stack was written in .NET, so that was a perfect match for us. But the issue was still that we needed to find a way how to expose different endpoints. Camera was a relatively easy thing to do because every game needs a camera, so that was pretty much done, but not fully. We needed also a way to simulate different things like sensor size, like focal length, like focus, or taking images sometimes that are not perfect, that are a bit grainy, that are in focus, out of focus, that can fail or simulate failure at certain times. For instance, even though movement of the camera was supposed to be relatively easy, actually making them while we were developing it, it showed as additional challenge, because there were quite a few different ways of how you can implement the movement. And when we put them all next to each other, we were shocked that the one that seemed the least natural to us was actually the one that we needed, because a gimbal that we were designing, or the other team was designing, was pretty much like a human hand. So each movement of your muscles, basically, or joints, will affect the other joints as well. So it would end up in a rather complex movement process. Yeah, and we also wanted to simulate things like having clouds in different positions or in random positions, having different background colors, having different times of days. We also implemented the ability that you can simulate where the tower is positioned. So for instance, if you position it at one place on the Earth, then the shadows will be falling in a certain way. But if you place it on another place on the Earth or position, then shadows will be different during the same time of day. And here we have some images of our simulator that we were able to take. So as you can see here, a background is a not solid color. So you can simulate rather different things, and you can make sure that AI will be able to at least deal with some of the issues that you might encounter in a real life. Now we have, so what did this help us do? It helped us to basically solve a lot of our problems, or to help us make every single meeting we had so much more productive, because most of the ideas we had during those meetings, we could easily test within a minute or two. So I would just press a couple of buttons and we would verify if that approach makes sense or not. Otherwise, we would basically choose an idea. We would then spend months on working on that idea. And then after a couple of months, we would went in another country, went on the field, test it, and then it would prove that the idea doesn't work and it would be back to the drawing table. This way, we were able to basically try it manually. So if you can do it manually, we will find a way to program it, right? And yeah, it helped us a lot to understand different mathematical issues behind this problem. Originally, we thought that these blades are going to be rather straight and that we can simulate them or approximate them with a straight line, and that these things are in parallel to each other, and that we can basically get away with a whole bunch of stuff. But when we loaded those 3D models into our simulator, it turned out, yeah, that will not work, as usually. But now we can switch to a video where we can actually see that simulator in action. And this is the application in front of that you can see that I'm using to control the simulator. So I can move it left, up. You can see that we have clouds, we can zoom in. There is a lot of data that we can display on the screen to help us diagnose what's happening, to see basically, yeah. And we could do some things that we couldn't do in a real life. For instance, the lens that we were using was limited to focal length of 150 to 600. In a simulator, you can go almost from 0 to infinity. So you can do whatever you want, and you can get a different perspective to see why some things are not working as you intended them to work. Yeah, so we were able to implement movements of the blades. You can see that we can rotate them around the axis. We can also rotate the entire hub, and you can see shadows dropping on the tower as they are passing by. So yeah, we had ability also. Let me just pause it again for a second. So why did we develop this remote app that you see in the front of the screen? To save us a whole bunch more time. Why? Because, yeah, even though we have exposed these things to be accessible through certain endpoints, and you could do that through not so user-friendly way, you would spend every time 5, 10, 15 minutes doing the same exact thing every time. But having, if you spend just that amount of time developing a tool that will help you, you will save so much more in the long run. So that's the idea behind this remote tool app, which is basically our Swiss Army knife. And we have implemented different things, like even ability to replay things you have done manually. So you could press record and you can do some stuff manually, move, change the focal length and so on, and then you can replay those sequences over and over again. Yeah, we also had the ability to talk with the simulator, with the real device, with the simulator and the real device at the same time, so we can test what's happening when it's integration time. And yeah, one thing to note here is that when you are developing games, you can use an integrated IDE to help you visualize what's happening. And you can also export the game and have it running in full resolution and full image quality. If you run it in full image quality, you would see that images are quite more crispier. Some of the artifacts that you can see here on the video are not actually present in the final output, but the IDE has its advantages as well, because at the end, it's written in .NET in C#, so you can place breakpoints. And also you can see what's happening in real life behind the scenes. Is the camera moving? Why don't you see the certain things? Are you actually measuring right the distance between the camera and so on? from the camera and the blade, and you have these widgets that can help you do that. And also there is a display that we have some clouds, and these things are quite random. And this is actually our algorithm now trying to zoom in and finish the scan of the blade. We are going to stop, the video is going to stop on its own in the middle of the scan, because now we are basically going to switch to a real life situation where we are scanning the entire blade from the beginning till the end. So if I go to next slide, at the end, So the other tools that I have mentioned, first one is the remote controller app. That app saved us so much time because it actually automated a lot of tedious tasks that we had to do manually, but it also helped us visualize what was happening with the algorithm in almost every single step. So we were able to see, okay, this was original image, this was image processed by AI, this is image pre-processed by our algorithm, and what we think that we see on the image. And these are some additional info that made that happen. So these pixels helped us think that, yeah, we should move one way or the other. And basically that became almost like a second nature for us. It's similar to when you are driving with somebody else in the car, you are passenger in front seat, and basically you are driving towards the red light. And if you are not feeling that the other person or the driver is not braking on time, then you get that feeling that something is not wrong. Something is not right, yeah. And we had the same thing, like we were watching and expecting algorithm to do certain things, and if it didn't, it would immediately run you a red light in your head saying, oh, something went wrong. And that helped basically that everyone was testing the algorithm the entire time while we were developing the application. Then we had like remote view that helped us optimize certain way we are using the camera. We also developed the PLC simulator. Why? Because again, the other team wouldn't be able to deliver that on time. So we needed a way, we had basically a specification of interface that we made earlier. So we implemented our own solution for that. That would just simulate different things. So when you send the command move to the left, he would increment internal counters. It would send you appropriate response back. And yeah, every single thing that we have built that wasn't meant for, that wasn't, let's say, originally planned in the project proved super helpful in the long run, because at the end, after 6 months of development, when the hardware was finally ready, it was produced in Friday, or at Friday they thought that it might be ready. I was supposed to travel on Monday, and I did travel on Monday, but on Friday, at the end of the day, they were not sure if the device is going to be capable for testing. So even on Monday, we were not sure will it work or not. So when I landed there, basically we had, I don't know, 20 plus bugs. And we were able to deal with those 20 plus bugs in just a day or two. Why? Because we have solved every single of those bugs before we even landed. So we just needed to make sure, okay, we have a simulated environment, we have the real environment, we have ability to send commands to a real device, we have ability to send command to simulated, and we also implemented the way to send to all of them or to both of them. And what that helped us is we basically send the command to both, we see what they do and what we get back. So if one is different than the other, we have an issue and we know where we have the issue. So it helped us deal with a lot of integration issues with just a couple of days. So in 6 months, we were able to do more than previous team did in a couple of years, just because of yeah, and you have to understand that also the reason why we were able to do that is because we went on site, but on virtual site, thousands and thousands of times. They had ability to go there like maybe 10 or 20 times. So we were in advantage there. And I'm now going to show you a video of how that looks in a real life. Yeah, just a perspective. You see that small dot in the mid at the bottom of a tower. That's a white van, and that was my office on wheels. And next to it is one-story building or one-story house, and you see how tall this turbine is. And we have to have a high-quality images from that huge distances or distances that are that great. And this is actually the device working during our testing days there. On my screen, you can see basically what we see and what we visualize and what do we compare. And this time, instead of using the simulated images, now we are using the images that are actually coming from the camera. We are comparing them between different AI implementations to see which one is performing better at certain positions and yeah, visualizing every single thing that we can do inside of our application. Now, on the real images, you can see some defects on the blade that you could actually simulate in the simulator, but we didn't went that far. For us, the most important part was that we were able to simulate the general process or the general idea behind it. Now we will reach the tip of the blade. We are making sure that a blade is always in the center of the image, that it's fully zoomed, and so on. This is the actual device going back to its home position. Okay, so yeah, we can go to the next slide. Where is this data going to be used? This data is now used in VBI, and that's a whole nother topic that we could spend hours on talking on. But the general idea here is that we have a workflow where now you have to use a drone. You go on site, that drone flies and takes some images, and then you upload those images into our cloud, and then we do image stitching, finding analysis, detecting issues, and we produce the results or report. TMC would actually replace the first two steps here because, yeah, that's the idea behind the TMC. And here you can see how would actual output results look like. So we would have some stitched images, and you would have certain reports that on blade A, this distance from root, you have something that is defect or that you might want to inspect further or deal or fix or so on. So what did we learn in this process? First of all, help yourself succeed. How try to simulate as much things as you can before actually having to go on site to do some inspections, or help yourself verify that the things you are making are actually working, and help yourself troubleshoot those things. Meaning, how can you verify that the algorithm is actually working? How can you verify each single step in the process that you are making? And how can you involve every single person that's working on the project to be able to detect that something is wrong? And of course, it goes without saying, these all things should be done with the common sense, meaning you have to find the right balance. For us, we spent like 3 sprints on developing a simulator, and usually you can spend 3 sprints on nothing particular and lose that time when you could invest it in something a bit more useful. Thank you for your time. Do we have any questions? Okay, we don't have any questions. Bye.